Our speaker finally arrived all the way from Oregon, and Kathleen will introduce her.
Yeah, I'm really excited to introduce not only our youngest speaker, but one of the more further traveled. Meghana Rao is a 17-year-old high school student from Oregon. She has previously presented in Asia, and she has spoken to the president about biochar. So she just got off the plane a couple of hours ago, so I'm really happy to welcome you here. She has a very similar topic, but it's going to be very interesting to see the different directions they're taking on microbial fuel cells.
So thank you for having me here, and I'm sorry for if I caused any change-ups in schedules and everything. I'm sorry about that. So I'm Meghana, and I'm a senior at Jesuit High School in Portland, and my research was also about microbial fuel cells, and I focused on the cathode and incorporating biochar into that. I missed the last talk, so I don't really know how it relates, but I would love to know. So essentially, I'm sure everyone has heard about microbial fuel cells, and I don't want to be too redundant, but microbial fuel cells generate electricity through the flow of electrons from the anode to the cathode, and the oxidation occurs at the anode and the reduction at the cathode. And microbial fuel cells have many benefits as a source of sustainable energy production. They operate at low temperatures. They don't require much aeration or I guess technical work after they've been implemented, and they're currently being used to treat wastewater, and I know of a couple different places in Oregon where they're starting small test runs, so that's exciting. And essentially my research focused on the problem of the cathode, because currently the platinum cathodes make up approximately 60% of the cost of the entire fuel cell. And platinum is a precious metal, and it's energy intensive to mine, and the cathode itself is making people hesitant to scale up microbial fuel cells. And also, the performance of the fuel cell is limited by the cathode because the reduction of the oxygen to water that takes place at the cathode is not naturally very efficient, so the platinum also acts as a catalyst in that sense. So the U.S. Department of Energy has proposed a goal of reducing platinum usage in all fuel cell cathodes by a factor of 20 or replacing it altogether, and that is where that's what I heard about, and that's what I wanted to try and tackle. And so the challenge is to find a cheap and efficient material that can be used as a cathode. So how is biochar connected to this? So biochar is, as we know, pyrolized organic material, and generally a soil amendment. And for the past 2 years, I did research on biochar's stability in the soil, looking at what different factors affect its degradation rates. And through this, I knew that biochar had certain properties that could make it a potentially viable cathode. So when I wanted to tackle this cathode problem, I actually immediately thought of biochar just because of my previous work. Because biochar has a high surface area, a porous structure which could allow gas transport, water dissipation, and good proton and electron conductivity. And biochar is the beginnings of the formations of graphene sheets. So these properties are what made me want to see if I could make a cathode out of biochar for a microbial fuel cell. So my research objective was to design and test a feasible and sustainable cathode for a microbial fuel cell using biochar. So to do my research, I first obtained my various biochar samples. I had a total of 7 different chars I was testing. 3 pyrolized at 670 degrees Celsius, so mixed wood chips, Douglas fir, and yellow pine. And these samples were from the International Tech Corps. And then I also got 4 samples pyrolized at 1,100 degrees Celsius, made out of Arundo donax, which is a very fast-growing grass in Corvallis, Oregon, that people are trying to do something useful with. Douglas fir, brewer's grain, and digested plant fiber, and these chars were from the Environmental Protection Agency. And once I got my 7 different chars, I crushed them down to less than 63 micrometers using a coffee grinder to maximize my surface area. And then I went on to design the cathode. So probably probably the most difficult, and the next step of my research was developing a smooth, like, polymer catalyst that I could spread on a surface. So generally the surface of the cathode is a carbon cloth maybe, but I chose to use a stainless steel mesh because it is significantly cheaper, and one of my goals was to keep cost in mind while I did my work. And so I was also using very commercial grade binders. So instead of Naphion, I was trying like a synergetic combination of ethanol and polytetrafluoroethylene. So a lot of my work was just focused around finding out how much, it was kind of a trial and error process of finding out how much binders I needed to mix with the biochar to get a polymer that would not crumble or sever as I spread it across this and would not allow water to seep through it. So this was probably like the biggest engineering part of my project. And once I figured out that ratio of binders to biochar, I was able to assemble the cathode. So I would add my biochar to the binders, heat it for 1 hour, and then apply it to the stainless steel mesh, and then cut out a small testing circle. And I tested my cathodes in an electrochemical test cell connected to a potentiostat, which was essentially just testing linear sweep voltammetry on the cathode. And I had a control, which was a traditional platinum cathode. And I was applying a voltage of negative 0.3 to 0.3 volts, and each test took me about 3 hours. And these are just some photographs of the cell, and it's kind of difficult to see, but in the little petri dishes are the cathodes drying, and in where that washer is, in that kind of dark circle, that's the cathode. I mean, it's black, so it kind of just looks like black space, but that's where it is, and it is connected to the potentiostat in these pictures. And so this is my data, and so on the left, there's the graph of the biochars pyrolized at 670 degrees, and then on the right, there are the graphs pyrolized at 1,100 degrees Celsius, and the black line in both of the graphs that is the same, that is the platinum control. And so the range of interest that I was looking at was between 0 and 0.1 volts, because that is traditionally where the cathode operates in this model. And so as it can be seen, the platinum had a range of about 5 to 12 amps per meter squared, so I was looking at current density. And if you look at the 670 degrees biochar cathodes, the current density was very low. Some of them were close to 0, some of them were like 0.1, some got near about 2 or 3 amps per meter squared for the 670 degrees Celsius, but I was not seeing very significant performance. However, for the 1,100 degrees Celsius, you can see the distance between my data lines and the controls has become smaller, which means that the cathodes were performing better because they are getting closer to the performance of the platinum cathode. So the red line, which is the closest, was the Douglas fir pyrolized at 1,100 degrees Celsius, and its current density range between 0 and 0.1 was, I believe, 2 to 4.9 amps per meter squared. And while that is still not comparable, maybe to say to 5 to 12 amps per meter squared, it was definitely better than 0.1 amps per meter squared or 2 amps per meter squared. So it was showing that it could operate. And here are all the numbers in a table and all the data combined. So as it can be seen, the Douglas fir was 2.02 to 4.9 amps per meter squared, whereas some of the other cathodes were 0.07 to 0.27 amps per meter squared. So there was a significant difference between the higher temperature pyrolysis and the lower temperature pyrolysis and the feedstock. And so temperature and feedstock were affecting the performance of the cathode. And while none of them performed close to the platinum, you could see that different factors were improving performance, showing that maybe the performance of a biochar cathode could be improved even further. And then I also did a cost analysis per meter squared of a platinum versus a biochar cathode, which may not be a fair comparison because we're talking about platinum and biochar, but overall, per meter squared, a platinum cathode is $1,500, whereas a biochar cathode using the materials I used would be $24 to $44. So even though the Douglas fir cathode was operating at about 40% of the platinum cathode's efficiency, it was 50 times cheaper. So I guess hypothetically, if someone was trying to scale up, a biochar cathode might be a viable option in that case, because you'll be able to produce more overall. And so from my research, I saw that biochar can function as an inexpensive and environmentally friendly cathode. However, there are still a lot of questions left to be asked and a lot more research to be done on this. So as I saw, the cathodes made with biochar pyrolized at the higher temperature, the 1,100 degrees Celsius, had the higher current densities as opposed to the 670 degrees Celsius pyrolized chars. And feedstock was affecting the current densities, so Douglas fir was outperforming the yellow pine and the mixed wood chips. And as I saw, the Douglas fir cathode, even though it was only 41% as efficient as a traditional platinum cathode, it was 50 times cheaper. So there are different factors that need to be, I guess, considered in as I take my next steps forward. And so some of the limitations of my research were that the feedstock that I had at the 670 degrees Celsius and the 1,100 degrees Celsius were not the same, unfortunately, because I wasn't able to coordinate that properly. It was a little bit difficult, so there was a little bit of inconsistency in, I guess, the controlling of my experiment there. And I only tested one possible design of a cathode. There are likely many different ways someone could approach making a biochar cathode, and I only tried one way. And also I tested my cathodes in a controlled electrochemical test cell, which solely takes into consideration the performance of the cathode, which is what I wanted, but it does not give an accurate outlook on how this cathode might perform in a microbial fuel cell where there are a lot more variables involved. And for the potential sources of error, one of the main ones is likely just how uniformly I was able to spread my biochar cathode across the stainless steel mesh. Even though that might seem a little trivial, the thickness is very important for it to be even, and since I was doing it by hand, no matter how hard I tried, there was likely to be variation for all of my samples. And I do not know how this variation affected the results, but I am aware that it was there. And so for future research, I would really like to try a broader variety of feedstock, because as I saw, some feedstock just have better potential than others, so I'd really like to investigate more to see if I can optimize this factor. And also one thing that's really important with these cathodes is durability and reusability. My cathodes were only tried 3 times, which is 9 hours of testing, which they held up through, which is pretty good, I would say. I mean, to me that was pretty cool, but in a real world sense, they need to be able to go for hundreds of hours without having to be repaired or replaced. So durability is extremely important, and that's something I would like to look at. And also, there was a huge difference between the cost of a platinum cathode and a biochar cathode. And I think it would be really neat to see if a middle ground could somehow be reached, where you aren't compromising efficiency, but you're also not spending so much money. So my goal would be to optimize both the cost and the performance of the cathode. And for a broader application, even though I was kind of looking specifically at microbial fuel cells, biochar cathodes may also be able to be implemented into other types of fuel cells, and they might have more applications beyond this. And so I would really like to thank Dr. Hong Liu from Oregon State University, Tony Janicek from Oregon State University, Dr. Marcus Klaber, Tom Miles, Dr. Johnson, Bill Petrich, and also my family, because everyone on this list has been extremely supportive of me throughout this process. For example, Dr. Honglu took me into her lab just after I wrote her proposal, and she didn't question me too much or anything, so everyone has been very supportive and has really let me investigate what I'm interested in. And just some references, and thank you guys so much for listening and for the opportunity to be here.
Questions?
Yes, I'm curious, how does the biochar compare to graphite or graphene? And how does the biochar compare to graphite and graphene in performance, and can you make hybrid materials with them?
That is something I'm really interested in. Graphene and graphene is being used in cathodes, and it does perform a lot better. It's a very good material, and it does a good job. However, it is more expensive than biochar, and since biochar does have the formations of graphene structures, I've always like toyed with the idea of, is it possible to isolate those more in any way, or so that's where I think maybe a hybrid could come across, but I'm not entirely sure.
Other questions? Is everyone just in awe of her?
Yes. This is a little off topic, but I've talked to Meghana a few times, and she has a really interesting story about talking about biochar to the president. So could you talk a little bit about that?
Yeah, sure. Okay. So I was very lucky to have the opportunity this past May to present some of my stability work on biochar carbon sequestration and how long it can be in the soil. I was able to present some of that work to the president at the White House Science Fair, which was very exciting. I got to speak with him for about 2.5 minutes, and he asked some really good questions, and it was just a very humbling experience to even be there and to talk to the president about research just beyond anything I could have ever imagined. And I got that opportunity through the Young Naturalist Award, which I won my sophomore year.
Wow.
I'd like to know what your career plans are.
Are you going to hire her?
Job offer.
Career, I'm not entirely sure. I love engineering. I love thinking in different ways, or like approaching things unconventionally maybe. I love connecting things that may not seem like they connect on the surface. So I like to think outside the box generally. So I think engineering is what I'm going to pursue. What field specifically, I don't know. I'm definitely wanting to stay involved in like environmental engineering, but maybe I'll take it from a chemical engineering approach. So I'm not entirely sure as of now, but I should figure that out.
Yes, question right back here. Can you please stand so we can record you? Thank you.
When you were discussing the square area of the cathode, is that of the manufactured finished product or of the biochar surface area?
That was of the manufacturer finished products, yeah.
Questions?
We're dumbstruck.
Yeah. We are all in awe still, so let's give her a hand of applause for coming all the way out here. And this wraps up our session, and if anyone wants to continue the discussion on MFCs, I'm sure that she would love to talk more, or at least congratulate her. So please, thank you. Have a good afternoon.